Hello everyone, and good morning. Welcome to the OneClass channel. My name is Fejiro, and I'm an Honors Bachelor of Science graduate currently working towards medical school. Today we'll be going over some commonly asked chemistry questions at both the high school and college levels. If you need some extra homework help or just some tutoring as well, please check out the links in the description below. And with that, we can get started right away with our lesson for today. And we're going to start with question number 1. Calculate the molar mass of salicylic acid, so that's C7H6O3, which is used to make aspirin. So the important thing here is to find the molar mass. We need to be able to add up the atomic mass unit, the AMU, of its constituents. What do I mean by constituents? I mean we have the carbon here, hydrogen here, and oxygen. So we know that salicylic acid is made up of 7 carbons, 6 hydrogens, and 3 oxygens. How they get that number? I'm looking at the subscripts for each atom mentioned, okay? So with that being said, we have 7 carbons, 6 hydrogens, 3 oxygens. I'm going to multiply each of them by their atomic mass units represented on the periodic table. So with that being said, for the carbon, we have 12.011. Okay? And for the hydrogen, we're given 1.008. And as a last one, oxygen, we're given 15.999. So now, let's multiply using our calculator to find each one. We have 12.011 times 7, 84.077. So we've effectively now gathered up all our carbons that's going to be in the molar mass of salicylic acid. Same thing with hydrogen here. We have 6.048. That's going to be all the hydrogens involved in the salicylic acid. And for oxygen, we have 47.997, I believe. Yep. And so we're going to add all these together. Because now, in a sense, we're just going to congregate all the numbers together so that we can get what salicylic acid's total is based on the constituents. So we have 84.077 plus 48 plus 47.997, and we get 138.122 grams per mole. This right here is going to be the molar mass of salicylic acid. So with that being said, let's see how we did. Exactly, they got their constituents. They have 7 and the atomic mass units of carbon. Same thing for hydrogen and same thing for oxygen, and they got 138 grams per mole. It's slightly different because they are using numbers based on a different periodic table most likely, or they're rounding, because right here they have 12.011. As long as the number is relatively the same, we know that we did it correctly. But on that note, it's very important that when you do solve molar mass questions, you preferably want to use a periodic table given to you by your instructor rather than trying to use a periodic table you just find, because the numbers do vary, and if your instructor is very specific on their answer, you'll be doing yourself a disservice by using other resources. So this is correct. And now I'm going to move on to question 2 for today. We have, how do you find excess reactants? To find excess reactants. So with this, it is a little bit tricky because the way excess reactant is based on the mole ratio. So there's two things here. It's not the mass, and it's not just how many moles each has. It's based on the mole ratio. For example, if I had so based on mole ratio, if I had A plus 2B turns into AB2, okay? For every mole I had of A, I needed 2 moles of B. So when I say based on the mole ratio here, I mean that this has to be kept 1 to 2. So if somebody said that, oh, I was given 0.6 moles of A and 0.8 moles of B, yes, B has more moles present, but it wouldn't be excess reactant. We want to see if it still has that ratio of 1 to 2. So I'm going to actually highlight that because that's very important. So the way we figure out what the ratio is that we want to get one of them to 1, preferably the smaller one, so we can kind of mimic what's going on with the ratio that's actually from the formula. And if we see here, we divide both sides by 0.6, we get 1A, but the B here is going to be 0.8 divided by 0.6, and we get like 1.3, or kind of like 4 over 3. Point being though is that as we see here, we have 1A, but it's not the same anymore. It's not 2. It's 4 over 3, which is less than 2. So because, as you see here, the mole ratio isn't the same, right? The side that's slacking here, that's not giving up the amount of moles that it needs, is a B side, because B should be giving 2 moles for every 1 mole of A. So in this case, even though we had quote-unquote more moles of B, B would be the limiting reactant and A would be the excess, because the A would be what's left over at the end of the day, because all it could really react here would be pretty much what half of 4/3 is. The reason why I say that is because that's the only way you can get that 1 to 2 ratio. So we would actually only use up 2/3 of A for that 4/3 of B, leaving you with 1/3 of A left of moles. So that is how A becomes the excess. So in summary, what I'm saying here, to find excess reactant, it's not just looking at the moles, and it's definitely not looking at the mass. You want to be able to look at the mole ratio, and the only way to really find out if it's excess is by comparing it to the original formula. So sometimes you either are given the formula or you have to construct it yourself. Either way, you have to refer to that in order to be able to find out what your excess reactant is because you're comparing the mole ratios. So with that being said, they actually have a more concrete example here. And as they said, they usually start by giving us the grams. If 6.3 grams of sulfur is reacted with 10 grams of oxygen, which will be the excess reactant? So as they see here, they have 6.3 grams of sulfur, and in order for, let me just check here, they're saying that in order for 6.3 grams of sulfur to react completely, they first found out how many moles were in that sulfur, hence the first step here, and then they converted the moles of sulfur to the moles of oxygen. Then they converted that back to the grams of oxygen, and they discovered that they needed 8.98 grams of oxygen to react completely with 6.3 grams of sulfur. But we're starting with 10 grams of oxygen. So if only 8.98 was used, that means that oxygen would be the excess reactant in this case. And just to be able to visualize that, because you want to see like what the mole ratio is here, we have 2 sulfur for every 3 oxygen. So the ratio here is 2 to 3. The sulfur given was 6.3 grams. And using the numbers here, so 6.3 divided by 32.07, we get around 0.196 of sulfur, okay? And then the oxygen, we have 10 grams, and it's 32, grams because there's 2 oxygens there. So 10 divided by 32, we get 0.3125 grams. And as we said, we divide by the lowest number to see at least what it is. And in this case, after we divide by the lowest number, we'll multiply by 2 to kind of compare with the original mole ratio here. So with that being said, we have 0.196 divided by itself times 2, and we get 2. And then now 0.3125, divide that by the 0.196, and then multiply that by 2, because that's how we got the 2 here, and we get 3.18. So as you can see here, they're not the same in terms of the mole ratio, and this 3.18 is greater than the 3 that's given on the other side. So with that being said, this would be your excess because it's not putting in more than it needs to compared to the original equation, and we would have here, as you will see, 0.18 moles, well, 0.18%, if that makes sense, because we have to convert it back to that 0.3125, but we would have a leftover amount of oxygen present in the in this reaction here. So that's what I mean here by mole ratios. So it's always important just to be able to break it down like that. Overall, this is correct. And now let's move on to question number 3. So for question 3, we have pKa of 2,4-dinitrophenol is 3.96. Okay, can you separate from benzoic acid using acid base extraction? So for this question here, I wouldn't even say memorize, but you would have to use your acid base table, because you do need to answer this question to know the Ka/pKa value of benzoic acid. So the way the pKa works is kind of giving you, in a sense, a range of not only where it would create like its buffer solution, but also it can be used as well to determine where, like, the amount of pH you need for you to protonate or deprotonate the molecule in question. So how it says it has a pK of 3.96, you need a pH less than 3.96, so maybe like pH of 3, for 2,4-dinitrophenol to be deprotonated and serve as and have its a conjugate floating around, because now you've done, actually no, sorry, pH of less than 3.96 adds more protons into the system, so we would actually have the HA of 2,4-dinitrophenol, so it would not be deprotonated. Now the thing is though, is that when you have a pH greater than 3.96, that is enough of a difference in concentration of protons, well, hydrogens floating around in the solution, for the 2,4-dinitrophenol to be deprotonated and end up with its conjugate base. So here, pH of less than 3.96, you still have 2,4-dinitrophenol floating around, and when you then increase the pH to the point to where you have it greater than 3.96, that's when the hydrogens start leaving the dinitrophenol to where you start having its conjugate base. So this is for dinitrophenol. Okay, now with that being said, we have now for benzoic acid. Let's first find it on our acids and bases table. And benzoic, there we go. It has, because we're working with pKa's here, as you can see, it has a pKa of benzoic. Okay, pKa is 4.19. So with that being said, that means actually that a pH of less than 4.19, we're dealing with benzoic acid's conjugate acid, which is just a benzoic acid. And then when you increase the pH to greater than 4.19, that's when you have deprotonated it, and now you're dealing with its conjugate base, as in more and more will start getting deprotonated. So with that being said though, as you can see here, we have this pH range, okay, and they're very, very close to each other. To be able to separate this from benzoic acid using acid-base extraction, the answer is yes. Anything is possible as long as the numbers aren't the same. But will this be easy to do? No. In fact, if you look at the sheet here, in terms of the different Ka's, we don't have many things. In fact, we have one that sits between benzoic acid and 2,4-dinitrophenol, and that's sorbic acid. And the way acid-base extraction works is pretty much that you want to be able to, in a sense, get to certain levels of pH to where one would be deprotonated and the other one stays protonated. So in this case, I would have to control in the solution, right, that I would have to control in the solution like a pH of literally 4 or 4.1 using like any methods I could. But the issue there is that although in that situation you will see that dinitrophenol would be deprotonated and benzoic acid would still be protonated, what actually happens is that we're not going to get much of a solution out. We're not going to get much of that dinitrophenol or benzoic acid out, because of the fact that just because you've, in a sense, passed these limits, these are more like soft limits, okay? If we were to put an actual picture of what we're dealing with, it's usually because, as I mentioned, pKa helps you kind of determine like the pKa kind of helps determine like the where the buffer solution works. It's actually more of a range of like a pH of 1 on each side. So we're really working with, for dinitrophenol, it'll be around 2.96 to 4.96, around there, to where it would kind of serve as a buffer, to where you have some that start to get deprotonated and others that still remain in its conjugate acid form. And the same thing for benzoic acid. We have a range of 3.19 to 5.19, around there. That is so much overlap that frankly, even if you put it to a pH of 4 to try to quote unquote separate them, because these are ranges, you wouldn't really get much solution out there. You'd actually, in fact, most likely get still a solution that still be mixed a little bit with some dinitrophenol and benzoic acid, because some of it would still be protonated and others will be deprotonated of each solution. If you're dealing with like a weak acid and a much weaker acid, for example, like if we had one that was a pKa of 1.2 and the other pKa was 9.7, this one would be fairly easy to separate because we have so much space to work with, where it's like between 2.2 and 8.7. We have so much space to work with that we know that those two are going to be completely separated. But this right here is so much overlap to where you can safely say that no. The answer is no. Technically, you couldn't. If you had the patience to really try to slowly extract, so like whichever amount would form, you could technically try, but at the end of the day, there will still even be some benzoic acids, even at the pH of 4, that would be deprotonated, because it's not a rule of thumb to like, I'm not going to change until this happens. Is that it's always going to be a buffer mixture where things are always moving the solution to where, you know, a proton might just attach itself to to the benzoic side, or it might just detach itself, and then now your solution is going to be impure because you still have a mixture of the dinitrophenol and benzoic acid. So yeah, if this was a real world situation, I would simply just don't waste your time, because you're going to struggle a lot trying to separate these two because of this. They're too close. So the answer is no, you can't. Okay, so as I said, 2,4-dinitrophenol and benzoic acid not solved in aqueous phase. That's typically what you find for most organic materials. And then, but the conjugate bases, like when you start getting the conjugate bases, usually like it attaches itself to a salt, like sodium, for example. You see that it becomes soluble in that aqueous phase. So it's that's how you separate them. It dissolves into the water, into the solution, and you can extract the solution because it kind of forms layers. But exactly, the issue with this is the acid-base extraction. The pKa is so close between the two that as you're trying to add, enough sodium hydroxide to be able to separate them, once you hit a pH of 4, you get both the dinitrophenol and benzoic acid into that solution, into the water solution, and then you still have some dinitrophenol and benzoic acid still in the non-soluble part, so it would not really separate well. So with that being said, let's move on now to question number 4. Okay, so we have what is the oxidation number of O? Number of oxygen. So this right here is a great question, because this is actually one of the things that you do have to memorize, because especially when you're dealing with finding the oxidation numbers of different compounds, you want to know the oxidation number of certain elements, certain atoms, because they do follow specific rules. So in this case, as it says here, so I'm actually going to read that because the answer there is fantastic. The oxidation number of oxygen is usually -2, okay? So whatever it's bonded with, typically, and I say whatever because there are a lot of different scenarios, but H2O, CaSO4, yep, and even like CO2, all of these, oxygen has an oxidation number of -2. Luckily for this situation, one of the rules as well is that hydrogen typically has an oxidation number of +1. And you'll see here that the reason why I wrote it like this is because you'll see that oxygen and hydrogen here balance out to where water is indeed a net, charge of 0. That's the goal here. So that's what you have to use these for. So oxygen is -2, there's 4 of them, that's -8. Now, SO4 by itself is SO4 2-, okay? So if it's SO4 2- and oxygen is -2 and there's -8 in total, sulfur has to be +6. And that's how we found the oxidation number for sulfur based on the oxidation number for oxygen, okay? Because that is one of the rules. Oxygen goes typically first. It's one of the first few that goes ahead, and it tells you the oxidation number for other molecules that don't have really much rules. So that's +6 there, which makes sense because calcium is also +2, considering that calcium is on the second column of the periodic table. Typically, you'll see that the oxidation number for alkali and alkaline metals are usually either going to be +1 or +2 respectively, and we can see that here. Things like carbon, sulfur, more things like in the gases area, or even not really transition metals, more so in the actually transition metals are good examples as well. Those things typically are, you have to find the oxidation number based on what it's surrounded by. So this carbon here, for example, O2 is 2-, that's -4. This carbon has an oxidation number of +4, okay? Now, I've said all this, but just like with everything in life, there's always exceptions. The there is one time that we know so far where the oxidation number of oxygen is not -2. At least the one that typically we address and care about. And that is when it's hydrogen peroxide. And hydrogen peroxide is known as H2O2, okay? The deluxe form of water. I'm kidding. That's not it. Don't drink it. I don't think it's even available like that. Point being is hydrogen peroxide, as you can see, just by adding in one more extra oxygen, it becomes a completely different thing from water. But here's the thing though, the reason why, and you'll see in terms of everything kind of ties together with oxidation number, what oxygen is actually doing and everything. In this case, hydrogen is still going to follow this rule of +1. And there's 2 hydrogens, that's +2. So now to balance it out, we need -2. Okay? And that means because there's 2 oxygens here, it has an oxidation number of -1. This oxygen in hydrogen peroxide is very different from this oxygen in like H2O, for example. Because of their oxidation number, it's working differently to share or take different amount of electrons than the oxygen in water. And that's key because, as you can see, hydrogen peroxide is quite different from water in terms of even what it does, of how it even, like, you don't water your plants to hydrogen peroxide if you ran out of water. You would pretty much kill your plants because this isn't the same oxygen anymore that it's dealing with. It doesn't break down the same way. You wouldn't get H gas plus O gas as easy when you 2H2 gas plus 1O gas. You wouldn't get this as easily as you would from H2O2 because our body isn't built to break H2O2 like that, unfortunately. So yeah, that is the issue there with hydrogen peroxide. And this right here is the only exception that we know, or at least list, to where oxidation state number of oxygen isn't -2. So with that being said, this is correct. And now for question number 5. Okay, we have, how is Ka calculated? Now, we have a bunch of different types of K, which is pretty much in reference to the solubility of that molecule. We have things like KSP and Ka. I think those are the only 2 that I can think of off the top of my head. And so KSP is usually dealing with solubility for like insoluble materials, pretty typically. So like when you have things like calcium oxide or something that's being formed, I think that's insoluble. But yeah, those things have certain KSPs. They have to calculate based on how much of it would actually still dissociate, because even if it's insoluble, you will find that there's still a little bit of dissociation that occurs in that solid. But when they ask for Ka specifically, this is the dissociation constant for acids specifically, okay? Because we also have Kb as well. Thank you, I just remember another one, which is just the dissociation constant for bases. So Ka is asking how much of this acid would separate into its conjugate base and H3O plus. So really, the formula we have here, and it's important to write this formula like this because it helps us set up how Ka is calculated. So we have Ha, aqueous, and that's going to be important, as you will see. H2O, liquid, dissociates to A minus, which is a conjugate base, plus H3O plus. Okay? So with this being said, okay, the key thing here is that Ka is calculated as products over reactants, right? But the products and reactions you don't add in are typically things like solids, liquids. You typically either are working with gas. This is not just for Ka, but like for K in general, when you find dissociation, like with gases and everything else, you would put gases there, but exactly, you don't put things like solids or liquids. And you'd also work with aqueous solutions. Reason why I mentioned this here, because in this aqueous solution, think of water like just what it's in a sense surrounded by. although it's reacting in this equation, it doesn't really take part in calculating the Ka, just because in a sense there's so much of excess of it because we're in a water system. So with that being said, we don't count water, so I'm going to pseudo cross it out. So as I said, products over reactants, we have Ka is equal to multiplication of products as A minus concentration and H3O plus concentration divided by HA. Okay, so this right here would be how you calculate Ka. Now, in regards to how you actually go about it, typically you would use ice tables. So initial change, equilibrium. A question would give you like a certain amount of HA, the concentration, so you know that HA, A minus, and H3O plus. You give a certain amount, so it'd be like let's say it was Q. Okay, and they would say yes, you're given this amount and it's dissolved. Well, I mean, it's not dissolved in the solution, but how much acid is produced when this HA dissolves in water. So you have that Q there, and because you haven't it hasn't dissolved anything yet, these usually typically start at 0, unless the question says we already have this much acid there, like H3O specifically. Typically everything else is 0, and then as you can see in this formula, for every X amount you lose, you gain 1 X amount for each. So you have Q minus X, and then you have X and X. And then as your, well, plus X is a change, and then you have X and X, and this will end up with Q minus X as the equilibrium. So considering that A minus and H3O both start at 0, typically you'd have both of them X's, so you usually would put, to find the Ka, it'd be X squared over Q minus X. Now, after this, it depends. You can either use a quadratic equation, or you can simplify this further based on the fact, like, just as how there's insoluble materials that still dissolve just a little bit, they're quite weak acids that dissociate and ionize, but the things that the amount that produces is so little and so insignificant that you pretty much still have just Q. So you can either use your quadratic equation to solve for that by rearranging, or you can just say X squared over Q, and then you just find the square root of Q times the Ka, and both of them would help you. Sorry, all the time solving for X, but this would be how you go about solving for X, which would be your H3O based on a given Ka. If you weren't given a Ka, okay, and the question said this much was produced, like this much of conjugate base and acid was produced from HA, the way you would then solve that is that you'd want to make sure that you have your amounts of conjugate base in H3O, and whatever starting amount they gave you for the HA, you want to subtract one of them, because as we said, every X is produced when minus X is subtracted. So if I said what is a Ka if 0.001 is made 0.001 of A minus and H3O is made from 1 mole of HA. So in reality, instead of it being just 1 mole, it'd be 1 mole minus the 0.001, which is quite small, but you still want to factor that in to really get that Ka value. And so we go ahead and say, based on this formula, we still have X squared over Q minus X. So we have X squared, which is 0.001, so we square that, divided by 1 minus 0.001, and then we know now that our Ka value would be 1, 2, 3, 4, 5, 6. It'd be 1.001 times 10 to the negative 6 in this theoretical case, which makes sense because that would show that this is indeed a pretty weak acid. So that would be how you do it. Exactly, like these still are your best friends just because you can still understand them. I wouldn't use this one then, just because we are finding Ka and not the actual X value. We don't need to use any quadratic formula. So with that being said, this right here will be how you calculate your Ka, and you're good to go. So as they said, it is products over reactants. They have CD over AB. They're thinking more exactly like K equilibrium, which is a general term for just the dissociation at equilibrium. But for Ka specifically, we're referring to a dissociation of an acid. So this is still correct, because at least it has a basic down of products of reactants, but Ka works just slightly different than just finding the KEQ. So with that, let's move on to number 6. So for number 6, we have write the electron configuration for P and Cl using SPDF and orbital box. And then they want us to describe the relationship between the electron configuration and its position on the periodic table. So let's start right away by doing the electron configuration first. So we want to make sure we do our whole off-bar principle, the 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. And I want to stop there, even though I could just keep listening to the whole thing, just because based on our periodic table, as soon as it loads, phosphorus and chlorine don't go actually that far. They actually end in the 3rd row, so we don't really have to go that extensively. With that being said, though, in regards to S, P, D, and F, if you look at the periodic table, if I just drew that like that, yeah, I've gotten pretty good at drawing a periodic table. Your first and second rows, which is going to be right here, this is known as your S orbital, and that is going to be indicated by just 2 electrons in that orbital, and you'll see because it only has first and second column. The one thing is that helium also counts as an S, so that would be kind of like the exception there, something you have to watch out for. The P orbital is going to be right here from like rows 13 through 18, not including helium. And as you can see here, when you count, we have 6 electrons there, so it's going to be in a total of 3 orbitals, because 2 electrons per orbital. So the S orbital only has 1 and the P orbital has 3, and because each of them can fit 2 electrons, we know 2 electrons are in S and 6 are in P. And then for the D orbital here, which we won't cover for this question, but just as a reference, it's going to be between columns 3 and 12, and that would be 10 electrons or 5 orbitals, and you can count actually through the periodic table. And then F, which we also aren't using, is going to be a lanthanum and actinium series, and that one, it's going to be a total of 14 electrons, which means you have 7 different orbitals in F. With that being said, the cool thing is that the reason why I mentioned that is because we pretty much just count through, and we have to make sure that we're referring to the right orbital. So hydrogen, it will be 1s1, helium will be 1s2. So for both chlorine and phosphorus, okay, we so far have 1s2. So for both phosphorus and chlorine. And so now we jump to the next row. We have lithium beryllium, that would be your 2s2. And then we have boron through neon. Remember, now that we're in our p orbital, that's 6 of them, so that's 2p6. So we've crossed this, and then we jump down to sodium magnesium, that would be 3s2. So we can cross that out. And now we're actually aluminum, silicon, phosphorus. So if we count it out, that's 3. So that's 3p3 for phosphorus, and chlorine are just 2 more ahead of that, 3p5. Okay, so these are the electron configuration using the s, p, d, and f. And in order to do the orbital box for phosphorus, so we have, as I mentioned, s is 1, p is 3, and this one only went down to the third shell, because that's the third row. So Cl, same thing as well. 1, 2, 3, 4, because this would be your s, and these are your p orbitals. Okay. And now that we've done it like that, what's going to happen here is that as we fill it in, as you said, it was 1s2, so we have like that, 2s2, and then 2p6, 2, 3, 4, 5, 6, and then 3s2, and then 3p3. So we have 1, 2, 3. So as you can see here, orbitals get filled halfway first, like 1 in each, and then it goes back and fills in again. And chlorine, the same thing here. 1, 2, 3, 4, 5, 6. And so we have 1, 2, 3, 4, 5. So now we have both the orbital box notation for phosphorus and chlorine here. Okay. And now the last question they ask is, what's the significance between this and its position in the periodic table? So this can actually be found through the superscripts of your full electron configuration. We have 2, 2, 6, 2, 3. If you added those numbers up, you'd actually get the element number for phosphorus. So 2 plus 2 plus 6 is 10, plus 2 plus 3, so it's 15 electrons we're dealing with, and phosphorus is indeed the 15th element. Because if you remember, elements are typically determined by the amount of protons they have, and if you have a certain amount of protons, as long as you're not dealing with ions, you would have the same amount of electrons, hence why it tells you where you are on the periodic table. Chlorine, on the other hand, you have 10 and then up to 17, so we have 17, and chlorine is indeed the 17th element on the periodic table. So that is how they relate. So let's see how we did. Yep, 3p3, and that's how they filled it halfway. It's perfect. And chlorine, 3p5, and that's how they filled it as well. Great. And exactly, they group 15 in periodic table, group 17, and it has 7 electrons in its third shell. Pretty much exactly, you should be able to, in a sense, find exactly what element it is, and based on the amount of electrons it has, as long as it's not an ion you're working with. So let's move on to question number 7. For this question we have, calculate either the H3O or the OH for the solutions below at 25 degrees. So calculate H3O and OH minus for solutions below. So we have A is OH minus of 1.31 times 10 to the negative 7. B, we have H3O of 9.35 times 10 to the negative 9. And these are all molarity. And C is quite high relative to the others. We have just 0.000715. And if we translate that, we have 1, 2, 3, 4. It'd be 7.15 times 10 to the negative 4 molarity. So, in order to be able to find this question, we need to know some formulas. And the reason why I say this is because I find this to be the most clear-cut way. We have first that pH is equal to negative log of the concentration of H3O. Okay? And then the formula we also have is 14 is equal to pH plus POH, because you'll see that if you add the pH and POH together, you should get the answer 14. So that's why you can rearrange it to where it's like, if you wanted to find POH from pH, you would subtract pH from 14. Okay, and we'll do that with these questions. And the last one we need to know is POH is equal to negative log of OH minus. The reason why this is important, because if we kind of just did like a slash here, you would see that after rearranging, you have 10 to the minus pH is equal to the concentration of H3O, and the last one, 10 to the minus POH is equal to the concentration of OH minus. So this is how we're going to keep kind of flipping around in order to get the answer. With that being said, first question we have 1.31 times 10 to the negative 7 moles of OH minus. So they want us to find the H3O plus. So in order to do that, we first have to find out the POH, because we're working with OH minus. So let's have negative log of concentration, which is 1.31 times 10 to the negative 7. Okay, and we get a POH of 6.88. So now in order to find out what that pH is, we just subtract that from 14. So now we have a pH of 7.11. Well, 7.12 if you round it. And now, in order to find out what the concentration of H3O is, we'd have to now use this formula here, 10 to the minus pH. So that's 10 to the power, okay, of negative that answer we got. And we get 1, 2, 3, 4, 5, 6, 7, 8. Just make sure I'm counting right, because I want to make sure I put 10 to the negative right answer. 1, 2, 3, 4, 5, 6, 7, 8. We have 7.6, because we only have two significant digits, so 7.63 times 10 to the negative 8 for the concentration of H3O plus. That would be for A. For B, now we do the same thing. We start with H3O, we want to get to OH minus. So now we first find out the pH by negative log of 9.35 times 10 to the negative 9. And we get that the pH is 8.029. And so to convert that, 14 minus that answer, POH is equal to 5.97. And then we do the same thing where we do 10 to the power of negative of that answer to convert it back. And we get, it's 1, 2, 3, 4, 5, 6. 2 or 3 decimal place, well, 3 significant, we have 1.07 times 10 to the negative 6, because that's what I counted earlier. 3, 4, 5, 6. And that'll be the concentration of OH minus. Okay, so as you can see, we're always using the kind of like these formulas here kind of work through, which is what we want. So for the last one, C, we have 7.15 times 10 to the negative 4. Okay, so with that being said, the pH of that would be negative log of that amount. So pH, exactly, which makes sense because it's such a high concentration relative to the others. We have a pretty low pH. That's a lot of acidic complex. So in order to find POH, is 14 minus that answer, 10.8, 85. And then now we do the conversion back, so that's 10 to the power of negative that answer. We have 1.39, well, if we round it up, 1.4 1.40 times 10 to the negative 11 for the concentration of OH minus. So that is what we did for these questions. As you can see here, we based it off of this, and we always made sure that we were solving for what we needed. So all these formulas were used here, and it's just kind of a simple, not simple, but it's important that you go step by step so you don't miss anything in this question. With that being said, let's see how we did. We have 7.63 times 10 to the negative 8, 1.07 times 10 to the negative 6, and 1.40 times 10 to the negative 11. So this is correct. And now move on to question number 8. What is the oxidation number of carbon in CO2? So for this, in order to solve this question, you have to understand what the oxidation number of oxygen is. And now you're probably thinking like, okay, well, how do we figure that out? This is one of those you have to memorize, because the oxidation number of oxygen is typically -2. And the only time so far that we note where it's not is when it's with hydrogen peroxide, okay? And that right there, oxygen is -1. But in every other situation where oxygen is bonded with something, oxygen serves to be -2. With that being said, we have CO2, okay? Carbon is attached to 2 oxygens. So we keep the oxidation number for oxygen the same of -2, but there's now going to be, in total, -4. But CO2, as you remember, is actually a total net charge of neutral. Okay, it's not an ion, it's just a molecule. So in order to balance it out, carbon needs a charge of +4. Okay, in order to make these balance out. So with that being said, carbon, if we now translate it back, because it's only one carbon, as you can see here, I kind of went in a direction like this, and then that's how I was able to come about it. We have started out with a -2, there's 2 of them, so -4, and the carbon needs +4 to balance it out, and it's only one carbon. So with that being said, oxidation number of carbon is +4 or 4+. Either way, it's just an increase of 4, okay? Because you wanted to balance it out. And exactly the key here, as they also say, the answer is 4+. The key here is understanding that oxygen and certain other elements follow specific oxidation rules, and you use those specific rules to now answer the ones that don't follow specific rules. In this case, oxygen is 2- unless it's with hydrogen peroxide, which it wasn't, because we were doing carbon dioxide, and so that's why we went with 2- to solve for 4+. And now, question number 9. We have define formal charge and explain how to calculate it. What is the purpose of the formal charge? So now purpose, and organic compounds are composed mostly of carbon and hydrogen. Okay, but also may have other elements and atoms, and formal charges work very well for organic compounds when they're drawing the best Lewis structure. How do these satisfy the octet rule in organic compounds so as to have a formal charge of 0? So with this being said, actually we're just going to refer to the answer here because they do a pretty good explanation of it. I'm just going to highlight key points here, okay? Formal charge is a charge of an individual atom within a molecule or in a compound based on the electrons that it's holding or it's sharing, okay? So with that being said, okay, everything has its own like formal charge. Let's say we're dealing with NH3. Okay, this nitrogen's formal charge will be based on the electrons that it has by itself right here, and the electrons it's sharing, which are these three. Okay, now in order to actually calculate that, what we do, as they show this formula here, is the number of valence electrons. So nitrogen is known as, nitrogen has 5 valence electrons, and then we put a parentheses here, and then it says number of non-bonding electrons. I like to think of it as just lone pairs times 2, but non-bonding electrons, you just count exactly how many electrons aren't bonding anything, and so that would be that N. And I have it here plus because I put it in the brackets. It's going to be number of electrons shared in the bond, but divided by 2. Because if you're sharing them, you're really technically having one. You don't know which one you're having, but you're kind of having one of those two. Hence how you're sharing. So with that being said, the formal charge of nitrogen in this ammonia, if you just plug in the numbers, it typically has 5 valence electrons based on the periodic table. It has only one by itself that is not bonded to anything, so that's 2, well, one lone pair, so that's 2 electrons. And then here it's actually sharing in total, if you counted each bond is 2 electrons, 6 electrons is sharing divided by 2. So you have here that the formal charge of nitrogen is indeed 0. Okay, so that's perfect. That's just an example of what it does. If you're dealing with now NH4 plus, okay, so this is ammonium. Okay, you would see here that if we plugged it in, we still have 5 classes valence electrons, but nitrogen no longer has any that it's that it has by itself, no lone pairs, and it's actually now sharing 8 electrons. So 8 divided by 2, that's 4. So we have a charge of plus 1. So you will see actually that on the nitrogen, the formal charge of why ammonia is NH4 plus, as you write it out, is because the plus is actually on the nitrogen in that molecule, and we can show this by how we did the formal charge. With this being said, the purpose of formal charges is that the reactivity and stability of the atoms are structured can be tracked. The key thing is that they always typically want to follow a formal charge that has the most neutral charges. If they can help it or rearrange themselves, they would want it to where they have as many zeros as possible in that molecule, instead of having it like +2, -2 and such, because you'll still get a net charge of 0, but it just, if it's possible, preferably they would rearrange the bonds to where you have just a 0 and a 0. So exactly, and the last thing they address is the whole carbon, nitrogen, hydrogen, so 2 nitrogens, but carbon, nitrogen, hydrogen, and oxygen and chlorine, they satisfy the octet rule by sharing electrons with other atoms. And the key thing is here is that they do specific ways of sharing, and you'll notice that some things, I guess, yeah, they want to talk about the satisfying the octet rule. So some things will, depend on how they're bonded, will ignore the octet rule in order to get their proper formal charge, but that typically doesn't happen with organic compounds. Organic compounds are typically nice to where they can find a way to be able to bond with each other to be able to satisfy the octet rule and the formal charge. A perfect example of this would actually be like when you're dealing with acids. So if you had RC, this is just going to be like the carboxylic acid. Point being though is that the formal charge, if you actually solve for oxygen up here, in fact, it's 6 valence electrons, it has 4 by itself, and it's sharing 4 of them, and that's how you got 0. Okay, so with that being said, this one checks out. And in fact, if you saw that this oxygen got deprotonated, so you end up with like that, where there's a minus on the oxygen here, you would see here that it actually has a reason to be negative, because if you had 6, right now this oxygen has 6 electrons it holds by itself, and it has 1 bond, so 6 minus 7, That's how you got the -1. And you can see here that it actually shows as well that it's still following the octet rule. Everything is still good there, but the negative charge just had to go somewhere. And that is the best place you can keep it, because as you can see, carbon still follows the octet rule, this oxygen still follows the octet rule, and everything attached to the R and so forth follows the octet rule. So that's what it means. Like, there is ways to rearrange it to where you will satisfy the octet rule and make sure that there is only a formal charge when necessary. You're really trying to make it into a necessity rather than just making things, you know, plus minuses as many as possible. It's only like, if there's nowhere else for it to go, we have to put it somewhere that would make everything else feel at ease. So with that being said, this is correct. Okay. So now we have, what is a Lewis structure of formic acid? So actually, rather than answer this question, we're going to tackle this in our next video. So we're actually going to stop here. I just want to thank you again for joining me this afternoon. Well, this morning actually. If you have any more questions, you want to tackle more of these and just really understand, please check out our tutors and links in the description below. We're more than willing to help you. But with that, you have a wonderful rest of your day. Thank you for joining me this session, and see you next time.